Next, we will continue exploring the alternating series, and we will introduce a new idea or a new concept of the absolute and conditional convergence. So to get started, let's consider the following series, and you might have seen them previously, so we're not going to go over every single detail here, but by looking at all of this, you should be able to recognize them as alternating series, and therefore we should be able to apply for some of them the alternating series test and analyze its convergence. So the first series looks like this, and by the alternating series test it converges. The next series looks very similar to the first one, except we have a square root in the denominator, but in terms of the behavior, the terms are decreasing, and by the alternating series test it also converges. Now the third one, I guess, would be an outlier in this list, on this list. And why is it so? Because by the divergence test it diverges. So there's nothing really interesting going on when the alternating series diverges, but what I want to do next is I want you to focus on the first two and tell me if you can notice anything different between the one on the left and the one on the right while both of them converge. Is there anything different? And the answer is not trivial at all, but to actually notice that difference, we have to look into the series made of the terms obtained by dropping the alternating factor. So to understand the difference, let's consider the following series. And now, what do you see? We see that unlike the original alternating series, these two series actually have different behavior. So this series, the one on the left, converges because it is a geometric series, and the common ratio is 1/2, which is less than 1. That's why it converges. The one on the right actually diverges. Why? Because it's p series, and p is equal to 1/2, which is less than or equal to 1, meaning that this p series diverges. And the reason I said why the one on the right is an outlier, because just for the sake of being thorough here in our analysis, let's consider the series obtained from and I guess in order to make this always positive, let's make n equals starting point at 3. This series, of course, diverges as expected, right? So there's nothing interesting going on here at all. Now, so the difference between the two converging alternating series is in the behavior of the series obtained by dropping the alternating factor. And we actually acknowledge that difference by introducing the following vocabulary. So let's consider a series, alternating or not, doesn't matter. But let's say we have a series that already converges. And if we consider a series made of the terms of the original series by dropping the alternating factor, and that series converges, then the original series that is already known to be converging is said to converge conditionally. So again, this is the new term that we introduced. It converges conditionally, meaning it converges, but the series made of the absolute value of its terms, actually, I'm sorry, hold on. We say it converges conditionally if, let me fix this. If the series converges, then we say the original series converges absolutely. Sorry about that. And if the series of the absolute terms diverges, this is when we say that the original series converges conditionally. So the two terms that we introduced are converging absolutely and converging conditionally. So once again, if we look at this example, what's the difference between the series on the left and the series in the middle? They both converge, but the one on the left converges absolutely, and the one in the middle converges conditionally. And there is no such division for diverging series. If it diverges, it diverges. So again, that's why I said earlier that there's nothing interesting going on with the one on the right, but it's still good to put it side by side with the other two to see the bigger picture. And now the first thing that we need to learn is to identify whether we have an absolute or conditional convergence for a given series. So given this series, let's determine whether it converges or diverges. If converges, then determine if it's an absolute or conditional convergence. So this is the task. And first thing we do, we recognize this as an alternating series. Therefore, we are going to set up the alternating series test, and we're going to verify three conditions. 1 over n is positive, 1 over n is decreasing, and the limit of 1 over n as n goes to infinity is 0. Therefore, the original series converges by the alternating series test. And now we're going to continue answering the second question. If converges, then is it absolute or conditional convergence? To determine whether it is absolute or conditional convergence, we must consider the series obtained by dropping the alternating factor. So we have to consider this series. Now, as you recognize this series, this is an alternating series, it diverges. Well, we know that alternating series diverges, but an easier way, I guess a more formal way of justifying why it converges is to say that it's the p series with p equals to 1, which is less than or equal to 1. That's why it diverges. So, because the series obtained by dropping the alternating factor diverges while the original series converges, the conclusion here is that the original series converges conditionally. So we answered the question. Let's try another example. I'm going to use the same template. I'm just going to change the series. So we're going to clearly run a different test and maybe draw different conclusion, right? But overall, we're going to be following this procedure more or less, right? So let's try. We recognize this as an alternating series, so we're going to set up the alternating series test, and we're going to verify that this series is positive. That should be easy to verify. We're going to verify that this sequence is decreasing. You should be able to see that as n increases, the denominator increases, therefore the overall ratio decreases, and the limit of this expression or this sequence as n goes to infinity, you get 3 to the power n is infinity, infinity minus 1 is still infinity, and we get 1 over infinity, which is 0. So the conclusion is that this, the original series converges. How so? It converges by the alternating series test, and if it does converge, now the question we're going to answer, the second question, does it converge absolutely or conditionally? And for that we have to consider the series obtained by dropping the alternating factor, and this series converges. How so? Well, it converges by the limit comparison test that we learned earlier. And if you want to actually do all the work to convince yourself, we would compare this series with this series, which is a geometric series with the common ratio of 1/3, which is less than 1, and therefore it converges. So because the series made from dropping the alternating factor converges, we conclude that the original series converges absolutely. And we answered the question that was asked. Now, let's continue exploring this concept, and let's observe that if we consider any series and when the elements of the series or the terms of the series are always positive, so you don't have any negative terms, then by definition the the series will be exactly the same as the series obtained by dropping the alternating term, because there is none, and therefore the convergence will be synonymous to the absolute convergence. So if the series converges, it converges absolutely, and vice versa. If it converges absolutely, it converges. And the reason for that is because when the terms are positive, this is true. Now the question is, can we draw something similar for any series? And turns out that sometimes we can. So we have the following theorem. It says that the absolutely convergent series are convergent. So what does that mean? That means if you can show that the series converges, that will imply that this series converges as well. And if you remember, this whole conversation about the alternating series and absolute and conditional convergence was originally inspired by this problem. So here we had a series which is not alternating, so the alternating series test cannot be applied, but at the same time neither integral nor direct or limit comparison test can be applied, because it doesn't have all the terms that are always positive. So now with these new tools we can tackle this problem again. We can try to solve it again. So let's consider this series again, and the question we're going to answer is whether the series converges or not. And instead of trying to tackle this problem, we're actually going to try to use this theorem, and we're going to consider for a second the following series. So let's take the absolute value of all of this. Remember, if we can show that this converges, then the original series converges by this theorem. And if we play with this series, we can separate the numerator and denominator. And since n squared is always positive, there is no need to put the absolute value around something that is always positive. And now we can actually use the following argument. So the sign of n is bounded between 1 and -1, but if you take the absolute value of this, it will be bounded between 0 and 1, and when you divide it by n squared, it will be bounded between 0 and 1 over n squared. And if you take the limit, or I guess not the limit, but sorry, the actual series here, then you can see that our series that we're interested in is bounded above by the series that is actually p series with p equals 2, which is greater than 1, meaning that this p series converges. And that means we have a, again, this is like a squeeze theorem. We have a sequence of partial sums that has an upper bound, and it's increasing because now all the elements here are positive, and therefore this series in the middle must converge. So this series converges by what we actually call the direct comparison test. And what does that mean? That means we just concluded that this series converges. But this series is the same as the series of the absolute value. It's the same series as the series of the absolute value terms, and therefore by the theorem, this theorem right here, the original series converges. But remember, the original series was exactly this. So we found a way to prove that this series that puzzled us in the previous lesson actually converges. And in order for us to do that, we had to introduce the idea of an alternating series and the idea of the absolute and conditional convergence.